Good morning. Buongiorno.
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 Adesso non so chi c'è di... dunque, la settimana prossima si dovrebbe poter cominciare a fare la lezione in presenza. Quindi volevo sapere voi che orientamento avete riguardo a questo corso. Cioè qualcuno di voi verrà, non so, come siete messi.
Prof, io sono fuori di zona, per cui penso che continuerò a seguire online.
Ok. Cioè, nel senso che io sono disponibile ad andare a fare lezioni in presenza, chiaramente se c'è qualcuno, altrimenti continuo da casa. Comunque sia, vale sempre il solito discorso che io... Ah, ok, va bene, verrei in presenza. Ok, allora...
Anch'io verrei in presenza.
Ok, allora ci vediamo all'università, allora, ok. Quindi continuiamo come prima del blocco, e quindi facciamo in presenza e poi registriamo per quelli che stanno a casa. Cioè facciamo la lezione alla lavagna per quelli che stanno a casa, con la telecamera. Ok, so let's start. Ok. So let me see if it works. Yeah. So last time I think we derived and used already the canonical partition function, this function here, which is very important since it is the link between microphysics and thermodynamics, because I remind you that this function is related to the Helmholtz free energy by this relation. So once we have this function here, the canonical partition function, we have all the thermodynamics. And the canonical partition function basically contains, apart from some factor of normalization, as normalization factor, which, for instance, for particles which are free of moving in a certain volume V is 1 over m factorial times h to the power of 3n. But apart from this factor that one should include, the partition function is the integral over all the coordinates and all the momenta of the Hamiltonian e to the beta minus beta h. This is the partition function, and the distribution function rho is equal to e to the minus beta h divided by the partition function itself. Okay, where h contains, so it's the Hamiltonian, so therefore it contains the kinetic energy associated to the different degrees of freedom one has in his system, and in principle it can contains also the effect of external fields. We will see an example of, well, we already saw an example of this. Or it can contains also interactions between particles, and we will treat also this case, but not today. Now, this function here can be applied to any system in which basically the system is in contact with a reservoir in order to keep constant the temperature. Okay, so it's a situation in which the temperature is fixed and the volume is fixed. And we can apply this to a system of particles, of several particles, but we can also apply it to a system of just one particle, okay? Or just one particle. In a sample of particles, in this respect, I will call it ZC1, which means the partition function, canonical partition function for one particle. In this respect, one can see, for instance, a system, a gas, and pick up just one particle and consider this particle to live in the canonical ensemble and the rest of the system to be the reservoir. Okay. For just one particle, so this Z of C1, well, is the same quantity of before, so it's just that now we are integrating over dq1, dq3, dp1, dp3, the Hamiltonian of this single particle, which, if you want, in, let's say, Cartesian coordinates, is dr dp e to the minus beta h. Okay, and similarly, the rho, the distribution function, will be proportional, apart from the partition function, to well, e to the minus beta h, and therefore, by remembering which is the interpretation of the ensemble, I have that the number of states dn in a certain volume element dr dp, which is a portion of the phase space related to the particle, the single particle we are considering. And remember that rho has had the interpretation of being the density of states, in this case for a single particle in the phase space. Okay. Therefore, that this dn is equal to e to the minus beta h dr dp. Now, from here, I can do several things, in the sense that suppose that I have a uniform system and that the particles contains just the kinetic energy. H is just equal to p squared divided by 2m. In this case, I can integrate over dr and get the Maxwell-Boltzmann distribution. Because it's just e to the minus p squared divided by 2m times beta, then I integrate over dr, and I have a dp, which is p squared 4 pi. So I get the Maxwell-Boltzmann distribution, which provides the probability of having a certain velocity, no? But suppose that now we have a system in which the Hamiltonian contains, for instance, the kinetic energy and a potential energy that I call V of R. Now, in this case, I can, for instance, I can be interested in integrating over momenta this time, so over dp, and find the distribution in space of particles. So in the Maxwell-Boltzmann distribution, we consider a uniform system, just kinetic energy, we integrate over the volume, and we get a distribution in momentum or velocity space. But we can also, in presence of a potential, we can also integrate over momentum and find the distribution in space, this time, of the particles. And of course, this distribution or this probability or this density, I mean, it depends on how I normalize. Let's call it n of r, which is density of particles, which tells me how many particles I have in a certain volume picked in the position r. Now this density of particles will be proportional to e to the minus beta v of r. Okay? So there is a modulation, if you want, of the distribution in space due to the potential. So for instance, let me change page. Suppose, for instance, that we have a gas in a box and we have gravity. So in presence of gravity. Now, in presence of gravity, this function n, the density, will be a function of z and will be proportional, apart from a normalization factor, to e to the minus beta, the potential, which is itself a function of z, which is equal to e to the minus beta mg z. Okay? So there is a modulation of the density of particles as due to the external field, which in this case is a gravitational, is a constant gravitational field. So from here you see that if, for instance, the density at z equals 0 is a certain value and 0, when I look at the density in a certain position z above 0, there is an exponential suppression of the distribution. Okay? So, for instance, if I have, for instance, a mixture of gas with different mass, two gas with two different masses, for instance, two gas with masses m1 and m2. Now what will happen is that the kinetic energy associated to those particles, the average kinetic energy, is always kBT alpha, associated with the motion along the axis z. But the potential energy will be will be suppressed by the mass, if you want. So let's say that for m1 average kinetic energy is still kBT alpha, okay, for the motion along z. And similarly for m2 is kBT alpha again, independently from the mass of the particles, but while the first one will have n1 is of z is equal to n1 of 0 e to the minus n1 gz beta, the second one will have a distribution of this type, minus m2 gz beta. So you see that if, for instance, m2 is much larger than m1, of course there is an exponential suppression here, and therefore I will have more particles. If you want, m2 will basically stay close to the bottom of this box, no? Okay, so it's a way to select massive particles which will be at the bottom, if you want. the bottom of the box, and light particles will diffuse in a with larger values of z. Okay. Okay, so this is an exponential suppression. So if I write, if I make plot n of z, there will be an exponential suppression. This for m1, for instance, and this for m2. Okay. So basically, if you want the external field is a way to select particles, heavy particles, well, to filter, if you want, light particles or heavy particles. And we will see an example of this later also. Okay, so now let's continue with this sort of exercises of the canonical ensemble. And let me consider this situation. Sorry. So this is another exercise. Let me change page. Suppose that we have a cylinder with section A and length L. And, well, inside this cylinder there is an ideal gas of n particles. And suppose also that there is a constant gravitational field. Okay. The thing that we want to compute is the canonical partition function, the internal energy, and the specific heat, well, the heat capacity, which is just the derivative of U with respect to temperature. Okay, so first of all, one has to compute the partition function, Z of C. Well, this will be, since we are in presence of a gas of free particles, they are independent free particles, free in space, they are not localized, so I have to correct this with the usual Boltzmann factor and the h of 3n, which anyway in the calculation that I'm going to do will not play any role. And then I have the integral over all the coordinates and the momenta dq1 dq3n of the Hamiltonian, which will be e to the minus beta sum from e1 to 3. Okay, yeah. Okay, I can write this in this way. 3n pi squared divided by 2m. And then there is the piece of the Hamiltonian, which is associated with the potential energy, which is, in this case, is just gravitation, the gravitational field, constant gravitational field. So here I have a sum from 1 to n, for reasons that will be clear in a moment, mg. And let me indicate with q3i, which is the z coordinates of each particle. So let's say that 3 reminds me that I have just the Z component, and I is an index which runs over all the particles. Now, it's clear at this level that when doing these calculations, since I have non-interacting particles, the partition function associated with all the particles will just be the partition function associated to just one particle, then divided to the power of n and divided by n factorial. Okay, so basically I can see that z of c is just z of c1 that I indicated before, so it's the partition function for just one particle. Let me check if I introduce already this quantity in these terms, so I think so. Okay, I think so. This will be to the power of n, and then divided by n factorial. Okay. So basically what I need to compute is the integral over dz of this quantity here. Okay. So now here you have a kinetic part that will contribute with the usual factor, which is basically 1 divided by lambda to the power of 3n. Then when I have the integral over the space, over the volume, I will have an integral over the coordinates dx and dy for each particle, and then I will have a separate integral in dz for each particle. Okay, so let me be more explicit. Suppose that I have this integral dp1 dp3n of e to the minus beta I1 to 3n pi squared divided by 2m. Now this part will contribute with the usual 1 divided by n factorial, 1 divided by lambda to the power of 3n, that we derived already for the case of a gas of free particles in absence of external field. Okay, so those are Gaussian integrals, and one gets the de Broglie wavelength. Okay, and then there is the integral over dq1 dq what was 3n of e to the minus beta, let's say, potential energy. And basically what I see here is that when integrating over the x and y coordinates, I get A, because well, the section of the cylinder, because I just have to integrate over the it's a surface integral, no, with a constant function. So I will just get A to the power of n, of course, if I have n particles, and then I will have an integral in dz from 0 to L, and this is now a function that contains the variable z, which will be again to the power of n. Okay. So basically my partition function will have the following form. So this Z of C, now let me change page, will be 1 divided by n factorial, 1 divided by lambda to the power of 3n. Then I have the section to the power of n. If you compare with the case of a gas of free particles without any external field, I have a to the power n instead of v to the power of n, okay? In the case of no external field. And then I get this integral 0 to L dz e to the minus beta mgz, which is to the power of n since I have n particles. Okay, so this is just 1 divided by n factorial, 1 divided by lambda to the power of 3n, a to the power of n. Now you have to do this integral, which is e to the minus beta mgz, computed, well, divided by minus beta mg minus beta mg, and this must be computed between 0 and L, and then to the power of n. Okay. Now I think I need to change page. So therefore, when doing this integral, of course, I have the following structure, that z of c is equal to 1 divided by n factorial, 1 divided by lambda to the power of 3n, and a of n. When computing the function, the exponential function in 0 and L, I get 1 minus e to the minus beta mgl divided by beta mg. And this is to the power of n. Okay, so if you want to, so you see that this is just 1 divided by n factorial, z c1 to the power of n. Well, this z of c1 is just a divided by lambda 3, lambda cubed, and 1 minus e minus beta mgl divided by beta mg. That comes from the integration over just one particle, or the coordinates of just one particle, momenta and coordinates. So if I have n particles, I have this to the power of n. Okay, this will be used also later. So when computing the partition function of a system of particles which are not interacting between each other, I can just compute the partition function for one particles and then make it to the power of n in order to compute the total partition function. Okay. Now, once we have this function here, we have everything already. So we can do the thermodynamics, and so, for instance, we can compute the, well, the exercise was requiring the computation of the internal energy, and internal energy is the minus derivative with respect to beta of the logarithm of the partition function. Okay. Now, of course, here I will have several terms. Well, one is associated with the lambda to the power of 3n, and then I have another term which is, of course, associated with this beta that I have here. So I have to make the computation. Let me see how I do it. If I use some trick. Beta mg. Let me see what is better to do, eh? Yeah, okay. So here I will have minus the derivative with respect to beta. Let me collect this part here, the log of a to the power of n and factorial and lambda to the power of 3n minus the derivative with respect to beta of the log of 1 minus e to the minus beta mgl divided by beta mg to the power of n, so then I can put an n here outside. Okay. Now this term here will just provide the usual, if you do the calculations, since a to the power of n and m factorial do not depend on n, I will just have the usual log of lambda to the minus 3n, which I've done many times already. Well, not many times, but we have done it last time already. And this will contribute with the usual 3 half kBt n, which is associated with the kinetic energy. Okay. But then I have a minus, then I have this additional term here, this is 1. So I have minus n, the derivative with respect to beta of the log of 1 minus e to the minus beta mgl. Then I have a plus n derivative with respect to beta of beta mg. Okay. Now this term here is just n m okay. So this is n beta mg and mg. So this should be just n divided by beta. So this is the n divided by the beta, which means n times kBt. Okay, this will contribute with the n kBt. And then I have this term here, which is a minus n. Then I have 1 minus e to the minus beta mgl. Then I have a minus exponential of beta mgl, the minus. Then I have again a minus mgl. I think I get all the correct sign, I hope. Let me check if this is correct. Yeah, I think so. So therefore, by summarizing, the internal energy in this system U is 3 half kBt n coming from the kinetic energy as usual, plus there is this additional n kBt that comes from the integral, well, from the previous calculation. Then there is a minus n mgl e to the minus beta mgl, and here in the denominator I have a 1 minus the exponential of minus beta mgl. Okay, so I think that that's it. So this is the correct calculation without any approximation. Okay, and well, now here I have separated these two terms because one was coming from the kinetic energy and the other one from the integration of the potential energy. But now I can put them together. So this is 5/2 kBtn minus the other term, n mgl, and 1 minus e to the minus beta mgl, and I have e to the minus beta mgl. Okay, so now in the limit, so this is u, in the limit in which L is large, so for large enough L, for large enough L, now this exponential, so this term will go to 0, no? Because, well, will be exponentially suppressed, and therefore U will be this 5/2 kBtn for large L. And CV will be just the derivative of U with respect to T at constant volume, and therefore it will be a 5/2 kBn. So what I notice from this calculation is that the heat capacity for a gas inside an external field is larger. So even though the number of degrees of freedom is the same, because I have n particles in 3 dimensions, and I have an additional external field, but the number of degrees of freedom is the same, okay? Same number of degrees of freedom as in the case of no external field. But the heat capacity is larger. Is larger by an additional kBt, an additional nkb term. So that means that the presence of a potential increases the heat capacity of the system. Larger heat capacity means that if you provide a certain energy to the system, heat for instance, the temperature will be the variation of, so the larger the heat capacity, the smaller the variation of the temperature. And if you want, this result can be justified by noticing that since we have potential energy also, not only kinetic energy, when I provide energy to the system, or if I remove energy from the system, I can convert this energy not only into kinetic energy of the particles, but also into potential energy. So if I provide energy to the system, I will increase the kinetic energy, but also part of this energy, external energy, will somehow be stored, if you want, in the potential energy. Okay, so that's why the temperature, the variation of the temperature will be smaller with respect to the case of no external field. Okay, and of course the same holds true when the system is providing energy to the environment. So also in this case, it can provide much, so larger, if you want, you can provide a certain amount of energy without a significant change of the temperature, since you still have this potential energy, which is another source of energy, if you want. It's more or less the explanation of this effect. And I want to notice another thing, which is the following. Let me take this one. Diciamo questo. That when considering the product in the partition function of one particle, I had A1 minus e to the minus beta mgl divided by beta mg. This is in the canonical partition function of one particle times some other terms. So what I want to notice that here, instead of volume, V, I have this factor A, which is a surface, times this quantity here, which, if you want, can be interpreted as a sort of effective length. Okay, so let me consider L effective, this 1 minus beta mgl divided by beta mg. In the limit in which L is small, so if L goes to 0, then this is just L. Okay, this effective L is close to L because the exponential can be expanded and will be a 1 minus beta mgl, and beta mg cancels. So it just the effective length or height of the cylinder is just L for small l. Whereas if L is large L, I get basically a L effective, which is equal to kBt divided by mg. Which basically tells you that the height above which there are no particles anymore is provided by kBt divided by mg. So the larger the temperature, of course, the larger is the height in which particles can go or can travel. What I need to say about that, rather more than that, yeah, basically that's it. Well, another thing that I want to notice is the following, is that when I have a Hamiltonian like the one that I described before, for one particles it was p squared divided by 2m, and then I had a potential which was mg z plus mg z. Now suppose, so this is for one particle, one particle. Suppose that I want to compute now for many particles the same calculation, but in the microcanonical ensemble. In the microcanonical, I had to fix h between E plus delta divided by 2 and E minus delta divided by 2. So now, in the previous case, so in absence of external field, I just had a kinetic energy, and therefore it's just a sphere. So this is just a spherical layer. Without external field. Whereas in this case, since the formula is more complicated, there is the shape of the surface is more difficult, okay, to find, because there is this additional linear term. So it's a more complicated shape for the microcanonical calculation. Because there is this linear term, of course, here that makes the calculation, the microcanonical ensemble, difficult. Okay, so the volume in the phase space now is not, let's say, trivial as in the case of a Hamiltonian, which does not contain external fields. Therefore, it's much better to use the canonical ensemble. Okay, this is the story. Let us make another exercise, again along the same line. So suppose that now we have a gas in a rotating cylinder. And we will find the partition function, canonical partition function as before. And what we will see is also to find the ratio between the number of particles, well, actually the distribution, if you want, distribution of particles within the cylinder. And in particular, we will see how, again, one can use an external field, in this case, due to the centrifugal force, to separate different components of a gas, of a mixture of particles. Okay, so it is, again, an exercise that one can do with the canonical ensemble. The thing is that now I have a cylinder which is rotating, so I have no external, so I have no gravitational field, but I have a cylinder which is rotating with a certain angular velocity omega, which is omega z versus z. Okay, so here I have z, here I have x and y. And the calculation clearly is better performed in cylindrical coordinates. Let's work in cylindrical coordinates. Okay, so the only thing which is different with respect to the previous case is that now I have a sort of an external field which is provided by centrifugal force. So in a system non-inertial system, which is basically the system of the cylinder, I have in the system, I have that each particle feels a centrifugal force. If I sit in the cylinder, inside the cylinder, no, in a non-inertial frame, and the centrifugal force Fc is provided by the formula, the standard formula, which is minus omega times omega times r, and I have the mass of the particle here, m. Okay, so now, okay, you can do the calculation, by just noticing that, so you can compute omega cross r, which will be something like this. I will not do the calculation in detail because you already done those things in general physics. Now the coordinates in spherical, the x, y, and z in spherical coordinates will be just those z. So here I have r cos theta, and here I have r sin theta. Okay, where what is theta? Theta is this angle here, this z, x, and y. Okay, so the position x is x is r times cos theta, and y is r sin theta. Okay, as usual. Okay, so you do the calculation, blah blah blah. You do the cross product of omega times the omega cross r, and then you will see that the centrifugal force F of C is just the standard omega r omega squared r m r versor. Okay, if you do this calculation, so you have the centrifugal force is as a modulus, which is m omega squared r times r versor. Okay, so it's centrifugal as usual. Now, since I have this force, I can introduce a potential associated to this force, which is a centrifugal potential, which is provided by the following formula. Vc is minus 1/2 m omega squared r squared. Why is this? Because if I do the derivative of Vc with respect to r, this is a minus, and I do the minus derivative of Vc with respect to r, then I get exactly m omega squared r, and this is basically the r versor component of the force. Okay, so if you want minus derivative of Vc with respect to r versor, which is one component, the radial component of the gradient of the potential, is just the centrifugal force F of C. Okay. So the thing is that now I have an additional potential in the Hamiltonian, which is this Vc, that must be taken into account when computing the partition function. So in particular, now we can compute Z of C. Let me see how I did it. Okay. Z of C, again, as before, I have to change page. Z of C, as before, will be 1 divided by n factorial Z C1 to the power of n. Okay, because I have independent particles, so non-interacting, independent non-interacting particles. So again, this will be 1 divided by n factorial and 1 divided by lambda to the power of 3n, which comes from the kinetic part. The Hamiltonian now for a single particle is p squared divided by 2m, and then I have minus 1/2 m omega squared r squared, okay, for a single particle. Okay. So now, okay, when integrating over the momentum, I get the usual lambda to the power of 3. For n particles, I have lambda to the power of 3n. But now the situation changes because I have also the integral over the volume V of the cylinder of the piece of the exponential with the centrifugal potential. So you have an integral over dr of e to the minus beta, the potential, which is e to beta m omega squared r squared. And I think, and there is a half also. Okay, there is a half here. Okay, and now this will be to the power of n, since I have n particles. Okay, now let me do this integral here. This integral is the integral over the volume of the cylinder, dr, of e to the beta m omega squared r squared divided by 2, which is equal. Now let's do the calculation in cylindrical coordinates. This will be an integral in the z from 0 to h, where h is the 8 of the cylinder. Let me make this is the cylinder, and suppose that this is h. And then I have 2 pi coming from the integral over the angle, 2 pi. Then I have the integral from 0 to r, where r is the radius of the cylinder, of dr e to the beta m omega squared r squared divided by 2, and then I have a Jacobian, which is r. That should be the calculation. This r comes from the Jacobian, from the Jacobian. Okay, so this is equal now to 2 pi h. Then I have e to the beta m omega squared r squared divided by 2, divided by beta m omega squared, computed between 0 and r. Let me check if this is correct. If I derive this quantity, I get the exponential, and then I have m omega squared beta. Yeah, that cancels with that. Okay, that should be correct. Okay, so this is again 2 pi h. Then I have e beta m omega squared r squared divided by 2 minus 1 divided by beta m omega squared. Therefore, finally, the partition function reads as follows. So the canonical partition function is 1 divided by n factorial, 1 divided by lambda cubed, 2 pi h, 2h pi, divided by beta m omega squared. Then I have e to the beta m omega squared r squared divided by 2 minus 1, and this all to the power of n. Okay, so this is the canonical partition function for this system. Okay, so from here one can derive the thermodynamics. which is trivial in the sense when deriving thermodynamics, in this case, once you have the partition function, it's just basically doing derivatives, okay? So it's not difficult. Now, what I want to study instead is the distribution of particles within the cylinder. As in the case in which we had an external field, which was a gravitational field, and we said, okay, since the kinetic energy is kBt half associated with the degrees of freedom, with the motion along the z-axis, I expect that there is a suppression of the number of particles for large altitudes, if you want, okay? And here it's similar in the sense that I will have an exponential, this time not suppression, but an exponential increase of the number of particles when I move far from the rotational axis. Because at the end, as I said before in the case, in the beginning of this lesson, I expect that n of r is equal to n0, so the density of particles as a function of the distance with respect to the radius, so r, sorry, the distance with respect to the rotational axis, distance from the rotational axis, will be n0, which is the density exactly at the rotation axis, times the exponential of minus beta the potential, which is in this case is beta m omega squared r squared divided by 2. Okay. So there is an exponential increase of the density as I move far away from the rotational axis. Okay. Now this so this function here, well, this distribution actually is used in practice in order, as I said before, to separate different elements or different molecules having different masses. In particular, from here, the number of total number of particles n must be basically n0 times the integral over dr of r e to beta m omega squared divided by 2 from 0 to r. No, because to integrate over the radial coordinates, I integrated over the radial coordinate in order to have the total number of particles. So it will be something like this, okay? So this total number of particles. With some normalization factor, which is not important in this case. But in any case, suppose that we have a mixture of two gas. Two particles with mass MA and MB. Now I can compute that the number of total number of particles A divided by the total number of particles B will amount in calculating this integral. When computing this integral, I have an exponential minus 1 divided by beta m omega squared as before. Okay, so this is basically n. Let me see how I wrote it, and 0 and nb0. Then I will have, it's just the same integral as before, so e to the power of beta m a omega squared r squared if I integrate over all, so from 0 to r, and there is a half missing, beta m a omega squared, yes, minus 1. And similarly, I have the same exponential for particle B, minus 1. Then here I should have 1 divided by beta m a times omega squared. And here I should have a beta mb times omega squared. The integral as the one as before. So this beta and omega squared and beta omega squared cancel, and therefore I have this nice scaling. If I remove this, I have that if I want to write the density at the rotational axis as a function of the rest, NA0 divided by NB0 is equal to MA NA divided by MB NB. And here I have the ratio of these two exponential, which was beta MB omega squared r squared 1/2 minus 1, and similarly 1/2 beta MA omega squared r squared minus 1. Okay, so this is the ratio of the density at the rotational axis, and this will be equal to this factor here, which is the mass of particles A times the number of particles A divided by the mass of particle B times the number of particles B, and then there is this exponential function in this term. Now, if the exponential is such that it is larger than 1, so by neglecting 1, and this holds true if omega is large, or if you want r is large, or t is small. In this case, the exponential will explode, and then the ratio NA0 divided by MB0 will be equal to MA and A, MB and B, and here I have the exponential of 1/2 beta omega squared r squared, and here I have the difference in masses, so MB minus MA. Okay. Now this formula is this formula and this technique is used to separate elements, elements, because you see that massive particles will tend to move close to R, whereas light particles will be closer, if you want, to the rotational axis. For instance, suppose that MA is smaller than MB. Suppose that MA is smaller than MB, and suppose that NA is equal to MB, so I have same number of particles. Now I can have that NA0 divided by MB0 is much larger than 1 if, of course, MA divided by MB times the exponential is much larger than 1, but when this is obtained, when omega is large, or R is large, or T small. So if I have a mixture of gas in a cylinder and I increase a lot the rotational energy, then you see that I have an exponential explosion here, and therefore I have that the ratio between the density of particles along the rotational axis is much larger than 1. In particular, the density of particles A is much larger than the density of particle B. Okay, so there is a selection. Okay, massive particles will go to the edge of the cylinder with an exponential increase, whereas light particles will basically stay closer to the rotational axis. Now, of course, if A is, for instance, uranium-235 and B is uranium-238, you see that this centrifugal cylinder, the system operates with a centrifugal separations. In a rotating cylinder. So therefore, the system in particular, you want to build up a centrifugal where powerful enough cylinders, rotating cylinders with high values of omega, and in such a way to separate, for instance, the uranium-235, which will be closer to the rotational axis, whereas uranium-238 will be will distribute more likely at the edge of the cylinder. Okay, so then when you heard about program of enriching uranium with centrifugal by use of a centrifugal force, basically the principle is the one that we explained before. Okay, it's a mixture of system of two particles at a certain temperature, and due to the centrifugal force you can separate the two components. Okay, by exploiting, if you want, the potential energy. And I think that we will make a stop for 5 minutes, because now it's 10:20, and we will continue in 5 minutes. Okay, may I continue?
Yes, and I also have a question, Prof.
Yeah.
I was asking myself if, as we said in the previous exercise, we have an enhance of the specific heat in presence of an external field. So is this purely theoric, or do we observe this actually in real life?
No, no. I mean, it's not theoretical in the sense that if you, it's in practice is correct in the sense that I mean, it's intuitive, no? In the sense that if you have the possibility to store energy in gravitational potential energy, it's clear that the temperature, the variation of temperature is smaller. So if you have, suppose that you have a gas in a box without external field, when you provide energy to this gas, for instance, by heat source, the only, let's say, way the particles can react, if you want, is to increase their kinetic energy. Okay, so the kBt will be larger, no? kBt half. Whereas if you have also a possibility to store part of this energy into the potential energy, so you can, it's like having more degrees of freedom effectively, because basically you can have that the particles will gain potential energy by keeping their kinetic energy the same. I don't know if this clarified more or less or not. It's like having effectively more degrees of freedom in which you can store the energy of an external source. I don't know if this is clear. Maybe
Yes,
yes, maybe
thanks.
not. Or I mean, differently, if you have, of course, if you have particles with a certain temperature and with a profile, then of course, when this system releases heat to another system, this heat can come from the kinetic energy, but also the potential energy. So you can, since you have potential energy, you can, no, as usual, convert kinetic energy into potential energy. Sorry, since I am at home, I have to see who is. Sorry, just a moment. Sorry. Since we are all at home, sometimes happens that someone rings. So basically, the fact that this external field is a gravitational constant field, a constant gravitational field, or harmonic potential as the one that we saw last time, does not change too much, in the sense that if you have a potential which is quadratic in the coordinates, you know that the contribution will just be kBt half for each degrees of freedom, as we saw in the case of harmonic oscillators. If you have another external field with a different shape, then it will contribute in any case to the heat capacity with a different form, but in any case will increase the heat capacity. So it's not purely theoretical. It's like this. I don't know if this is clear, and it is also intuitive somehow.
Okay, perfect.
So I
Thanks.
hope it's okay. Okay, so now let's move to another thing, which again is related to degrees of freedom, which is the case of diatomic molecules. Sorry, I've done diatomic molecules. So up to now we have considered just monatomic, the case of a monatomic gas. So if we have an Hamiltonian with just kinetic term, just kinetic energy, and no potential. Basically, we have the 3 degrees of freedom corresponding to the fact that the particle can move in 3 directions. And these 3 degrees of freedom have 3 kinetic energy associated, which is pi squared divided by 2m for each direction, if you want, okay? Now, there's not much to do more than that, but now let's consider a gas of 3 particles without external field and without interactions among themselves, but in this case, let us consider diatomic molecules. So, the diatomic molecule can be represented in a schematic way in this fashion. So we have 2 points here, which are the atom, and suppose that basically due to the chemical bonds, this behaves as a sort of rigid body. Okay. Then plus we will see later that the position of the mutual position of the 2 particles can change, and this will be described by a sort of oscillator. So the oscillator takes into account the fact that the particles can move with respect to their equilibrium, okay? Deviation, if you want, from the equilibrium position. So we consider this molecule to be, as a first approximation, to be a sort of rigid body, and therefore this rigid body can have translational degrees of freedom. So if you want, the center of mass of this rigid body can move in 3 directions. So we expect that we have the usual 3/2 nkb T as a contribution to the internal energy related to the motion of the center of mass motion, plus we have the possibility of rotation, and to the rotation we will have 2 degrees of freedom associated. Because being a one-dimensional rigid body, so with a length but with no size, basically we have 2 independent ways to make the rotations. We cannot rotate along an axis which is parallel to the molecules itself. So this possible motion will not contribute, because we are considering just the length of the molecule, and we imagine that the transversal size is basically 0. Okay. So we have translational motion of the center of mass. We have 2 rotational degrees of freedom, which are the 2 ways in which this bar can rotate. We'll describe this in a moment. Then we have also the possibility of oscillation of these 2 particles around the equilibrium position, and this will be described just because we know how to do calculation as a sort of oscillator. Okay. Now, what we are going to do is to see that all these degrees of freedom, so the degrees of freedom associated with the rotational motion, with the translational motion, the degrees of freedom associated with the rotation, and the degrees of freedom associated with the oscillation of those 2 atoms around the position equilibrium, can be excited, but with a certain hierarchy in temperature, in the sense that here quantum mechanics will play a role. And we will see that while, for instance, the translational degrees of freedom are always excited, even at small temperature, to excite the rotational degrees of freedom and the vibrational degrees of freedom, which are associated to this oscillation, are excited at larger temperature. Vibrational degrees of freedom. Okay, so this is basically the idea. I don't know how much you have done about molecules in the course of structure of matter. I'm not sure about that, but anyway, we'll treat the thermodynamical part of this, and maybe you don't have you have not done this before. Otherwise, you just tell me if I'm telling you something which is known. But now, the aim of the rest of this lecture is to provide is to start to build this model of a molecule and to then study the thermodynamics of a gas of diatomic molecules. But the first thing that I want to do is to prove by using quantum mechanics that the translational degrees of freedom associated with the center of mass motion are basically excited. I always somehow excited. They are not frozen. Whereas we will see that the rotational degrees of freedom and the vibrational degrees of freedom are frozen at small temperature. At the end, we will derive the behavior qualitatively, the behavior of the specific heat as a function of temperature. Okay, now let's study first of all one, the translational degrees of freedom, or if you want, the motion in space in 3 dimensions of the center of mass. Now, what I want to do is to see which is the typical excitation energy of center of mass motion in free space. Even if we are talking of a molecule, we are just now considering just the center of mass of this molecule. Okay. And we will see that basically all the translational degrees of freedom are excited at normal temperature. Okay, so now to do this calculation, to do this estimate, if you want, let us consider the fact that when I have a box and I normalize, suppose that this box, this cube has L, the size of this box will be, of this cube will be L, and the momentum and the wave number are quantized by the following formula, no? By using the following formula. So the Kn is equal to 2 pi Ln, where n belongs to the natural number, and therefore the delta Kn is equal to 2 pi L. And similarly for the momenta, I have that delta P n is equal to h divided by L. So this, if you want, is the quantization of momenta. In a box. This comes from periodic boundary condition. On the Hamiltonian, or if you want, the kinetic energy. operator. No, if you have just kinetic energy and you normalize the wave function in a box, you know that the momenta are quantized with a quantum which is h divided by L. Now, E, the energy is p squared divided by 2m, therefore the delta E is something like p delta p divided by the mass m, okay? Therefore, delta E, and this is what we want to estimate the excitation energy of the translational degrees of freedom. DOF stands for degrees of freedom, usually. Now this the ratio, well, this delta P and delta P or delta Pn is not important to put n here, is h divided by L. And then I have a ratio between P and M, so 1 over M, and P is of the order again of h divided by L. So this is P, the minimum value of P, no, apart from P equals 0. Okay, the first value is this one. So therefore, this delta E is h squared divided by m L squared. Okay, so this is, if you want, the excitation energy for translational degrees of freedom. So now we will try to make an estimate of this in natural units. Let me take h bar squared and multiply by a 2 pi squared. Yeah, then I have here m L squared, and at the moment I have not done anything but for introducing the h bar. Now let us work in natural units. In natural units, I will have this 2 pi squared. H bar squared will be multiplied by c squared and will be this 200 squared MeV squared Fermi squared. And at the denominator, we have m, which is the mass, for instance, of a proton. So let's put just 1 JeV or 1000 MeV, mass of a nucleon. Actually, it's 940, but let's make things easier. And then what is L? L is a typical, it has a scale. Suppose that is 1 centimeter. So L 1 centimeter, just to make calculation, which is 10 to the 13 Fermi. Okay. And so instead of L, I will put 10 to 13 Fermi, which will be squared. Okay, if I've done things properly, I should get an energy. And indeed, this is correct in the sense that Fermi squared cancel with this Fermi squared. Then I have MeV squared and MeV at the denominator, so I should get an energy indeed. Now, if you do the calculations, it's 2 pi. Let me check if this is correct. 1000, 10 to the 13. Yeah, you get a value which is of the order of 10 to the minus 23 MeV, which in terms of temperature, remember that 1 MeV corresponds roughly to 10 to 10 Kelvin. So in terms of Kelvin is of the order of 10 to the minus 13 Kelvin. Very small. So that means that, let me change, due to the fact that the box is large, 1 centimeter, it's a macroscopic scale, let me write it down, due to the fact that the box is large, it has a macroscopic scale, the excitation energy of translational degrees of freedom, is very small. And this also means that I can neglect, if you want, quantum mechanics for the translational motion. And therefore have that the contribution to the internal energy due to the translational motion will be the usual contribution. Okay, so the contribution of translational motion here we have rotational, and vibrational. And this will be the typical 3/2 kBtn. Okay? Associated with the center of mass motion. The standard value, okay? Why I'm here considering quantum mechanical correction? Because as we will see, this is not the case for the other degrees of freedom that instead could be frozen at small temperature. Here, the temperature at which the translational degrees of freedom are frozen is 10 to the minus, 10 to the minus 13 Kelvin, which is basically irrelevant, okay? So now, let us consider rotation now. So, and the possibility for this diatomic molecule to rotate. Now, let's see how to do it. Suppose that we have, let me make a plot of this. Suppose that we have here, so X, Y, and Z, our molecule. With the two masses here and here. And let's indicate, we project this bar on the plane X and Y, and we will have an angle which is phi, and then we will have another angle which is theta, okay, with respect to the z-axis. Okay, so you project your bar onto the xy plane, you determine the angle phi, the polar angle, and the azimuthal angle, which is theta, with respect to z. Okay. Now, so we are working clearly in spherical coordinates. And the spherical coordinates, we have r, so the radial position, theta, phi, and we will also have in the Hamiltonian formalism the conjugate momenta, which will be PR, P theta, and P phi. Now one can prove, I will not do it, maybe you have done it in the course of analytical mechanics, that since at some point I will have to integrate over the volume, well, I will have to integrate over the volume in space and the volume in momentum, which means integrate over the phase space. Well, at some point, I will go to pass from Cartesian coordinates for one particle to spherical coordinates. And one can prove that in this case the Jacobian is equal to 1, and therefore this integral over the phase space for just one particle will be the same, will have the same form in radial coordinates. So d phi, dpr, dp theta, and dp phi. Okay? This I will not prove it. So this is from classical mechanics. And this will be useful in a moment when trying to compute the partition function associated, well, the contribution to the partition function which is due to the rotational motion. Okay, so now we move on. Remember that we need to compute z of C1, which is the partition function of one specific molecule, which will contain, apart from some constant, will contain an integral over dr and an integral over dp of the minus beta, the Hamiltonian. Okay? Now we have already removed the part associated with the translational motion of the center of mass. We want to compute this quantity as it is the same quantity, but associated now to the rotational motion. Just the rotational motion in which theta can change and phi can change. Okay? So for a rigid rotation of a bar, we have that the Lagrangian is provided by the following formula that again I will not derive, and this was probably derived in analytical mechanics, and phi dot square. So these represent the Lagrangian of a rigid bar associated with the rotation of a rigid bar. So I'm neglecting here the translational motion because I have taken this into account already, where I is the moment of inertia with respect to an axis which is orthogonal to the bar and crossing the bar and passing through its center of mass. So this is the Lagrangian. One can derive also from the Lagrangian, one can derive also the Hamiltonian. And in particular, one has to compute p theta, which is the partial derivative of the Lagrangian with respect to theta dot, which will be I theta dot. And the p phi, the conjugate momentum of phi, which will be again the derivative of the Lagrangian with respect to phi dot, which is in this case again I sin squared theta phi dot. Okay, and out of this one can compute finally the Hamiltonian associated with the rotation. Let me put rot here just to stress that we are dealing with rotation of this rigid body. And when computing the Hamiltonian associated to the rigid rotation of this bar, one gets the following result: 1 divided by 2i. Then I have p theta squared plus p phi squared divided by sin squared theta. Okay? So now this is the most important quantity that now we need to to work with. So we have the Hamiltonian associated with the rigid rotation of this bar, okay? Now, in the Z of C1, so the canonical partition function for one particle and the contribution associated with just rotation, we'll have to some point, apart from some normalization constant that is not important at this level, I have to integrate over the coordinates, which is in this case are d theta and d phi and d theta. And sorry, let me put d theta from 0 to pi, then d phi from 0 to 2 pi. Then I have the integral over dp theta from minus infinity to plus infinity, and integral over dp phi from minus infinity to plus infinity of e to the minus beta h rot. Okay? And of course, there's no radial part here because I'm just considering rigid rotation, and I'm integrating over coordinates and momenta by taking into account what I said before, that when going to x, y, z, or if you want, x, y, z, px, py, pz, and going to spherical coordinates r, theta, phi, pr, p theta, p phi, the Jacobian is equal to 1. Okay? This can be proven in analytical mechanics. Okay, now it's a matter of computing this integral. Let me just sketch it and then I will stop. So ZC1 is equal to the integral over phi is just 2 pi. Then I have the integral over dp theta. Let me sketch it here. dp theta.
Prof, il foglio.
Il foglio. So ZC1 is equal to 2 pi. Then the integral over dp theta of e to the minus p squared theta divided by 2I beta. This is just equal to the usual, this is a Gaussian integral, so is pi 2I divided by beta. So then in the partition function, I will have this term, which is 2 pi I divided by beta. And then this integral from minus infinity to plus infinity over dp phi of e to the minus p phi squared divided by 2I sen squared theta. And then I have beta here. And this is also equal to pi 2I sen squared theta divided by beta, that I can include also here. So you have a pi 2I sen squared theta divided by beta. I think I have all the calculation almost done, but then this must be integrated over the phi, over the theta, because I have not done this integral. Okay, up to now, okay? So I have integrated over phi, and I get a factor of 2 pi. I have integrated over dp theta and dp phi. Then what is left is this integral over d theta. So z of C1 is equal to 2 pi. Then I can remove, well, I will have 2 pi I divided by beta, 2 pi I divided by beta. Then I have the integral over sen theta d theta from 0 to pi. which is equal to 2. So finally, I will have a factor of 8 pi squared I and a kBt, which is 1 over beta. 8 pi squared I kBt. So this is the partition function, well, the contribution of the rigid rotation to the partition function or canonical partition function of one particle. Now you see from here that when computing, and I will stop in a moment, so you can try to compute minus the derivative with respect to beta of the log of z of C1, and you will see that this will provide a contribution which is just kBt, which means 2 i's kBt divided by 2, which is basically associated with the fact that, again, also in presence of rigid rotation, I have to integrate over quadratic degrees of freedom, which has these two p theta and p phi, which are quadratic in phase space. And therefore, when I integrate, again, by using the equipartition theorem, I will get a factor of kBt half for each of them. And I stop here and continue next Tuesday. Ok, bye bye.
Buona giornata.
Grazie, buona giornata.
Buona giornata.